Howdy, folks. Good afternoon. So today we will begin with another concept, and the concept is that of flow rate. It's a very, very important concept. Flow rate means, or is, this symbol means defined by volume per unit time. Generally, it has to do with volume flowing over unit time. How much volume is moving around per unit time. And so you can see it will have units of something like meter cube per second, unit of volume over second. Okay. One can write, or actually I should write something like for volumes with uniform thickness, we can write volume equals the cross sectional area times d, the thickness or width. Once again, if you are seeing there is a blank space out here, there is a reason. I had people move out from here because you are not going to be able to read this part. And if you are not able to see, just move or go to the back. Just move or go to the back until you are able to see this part of the board. Unfortunately, unlike in the other classrooms, I can't slide this board up and down for you to see. So make sure you are able to sit in a place that you are able to view what I am writing. I cannot write beyond these 2 marks over here because the recording is not recording it. So volumes with uniform thickness, we can write volume as cross sectional area times d, which is the thickness. What do I mean by volumes of uniform thickness? Examples are cylindrical or rectangular pipes. Cylindrical pipe like this. This is the cross sectional area. Cross section. That is d, the thickness. Cross section means take the object, cut across it, a slice like that. That is a cross section. That is cylindrical. If it is rectangular, it would be something, say, like this. This, for instance, right there, that face, that is the cross sectional area. And then from here to there, this distance, or from there to there, this distance is the d. We cannot do that if the thickness is not uniform. We cannot, because then area is varying, right? Like imagine like a funnel like that. Which area would you take, this end or that end? Perhaps maybe average somewhere in between, but there are better ways to calculate those areas if you have to. But generally we can write, if it is a uniform pipe or a rectangular pipe, we can simply write cross sectional area times the distance. This implies we can write flow rate as volume per unit time, but I can write cross sectional area times sorry. If I take cross sectional area that way, this cannot be d. This is d. It is the other dimension. And this is definitely not thickness or width. It is length of the pipe. Please, there is no need to stand there or sit in the corner. There is space in over here, either there or go to the back. Be comfortable. There are some seats right there. Just find a space and move in there. Viewing from that angle will be very difficult for you. You will be uncomfortable. You can sit in the one of those last two rows up to the third row. If you are not able to see, let me know. I will write slightly bigger. I cannot write a lot more bigger because of space, but if you are not able to see, then there are space over there, plenty of spaces on that side. Okay. So, you get this point. So, flow rate will be cross sectional area times the length divided by the time t. This means flow rate is becoming what? What is that going to be? So, flow rate will become what? If it is a cross sectional area times d over t, what is flow rate going to become? What is that going to be? What was that? Exactly, velocity, that is distance over time. This is a very, very important concept. Concept number one, that flow rate is defined as volume per unit time, but it immediately turns out to be the cross sectional area times the velocity of the flow. So, if you know the velocity of the flow, This thing is so distracting, I don't know how to get rid of it. That's better. Anyway, ignore it. At times, we give flow rate a letter, a symbol. Instead of writing flow rate, right, we have to put in symbols. The symbol we use for flow rate is Q. But it isn't the symbol that is important. What is important is knowing what it is and how to get it. The fact remains that flow rate depends on the cross sectional area and the velocity of flow of the object, because it is ultimately a volume per unit time. It is necessary for you to know both, because you could be given the volume and you could be expected to use the concept of flow rate, or you may not be given the volume, you are given these dimensions and you are expected to find the flow rate. So, both ways are extremely important to understand. Good. Now comes the next concept. And I can write this concept here because it is such an important concept. Up to here will get recorded, I think. In incompressible fluids, the flow rate is always constant. I cannot tell you how important this concept is. You should highlight this as a very, very big important concept. I will explain what this means. First of all, let us discuss what do we mean by incompressible fluids. Incompressible fluids are fluids that under ideal conditions cannot be compressed. So, give me an example of a fluid. First of all, I do not think we discussed what is a fluid. I assumed you know what is a fluid, but what is a fluid? Or rather, perhaps, what is the difference between a solid and a fluid? Free flowing and yes, and correct. So, essentially the difference between solid, fluids and gases is the following. In solids, the molecules forming the object are tightly bound to each other in a fixed regular pattern. Pen. The molecules making up this pen are rigidly and tightly bound to each other in a fixed regular pattern. If this becomes a fluid, the molecules retain their character, but are now loosely bound, and therefore, can be easily moved around. Consequently, a fluid is anything which has the same property of the element. The molecular structure is still the same, but they are weakly bound and consequently freer to move around. A gas is the state of matter where the bond is even more weaker, and in fact, the molecules are not at all bound, but they are still the same molecule and they can just move around in whatever arbitrary directions that are available in the space. That is a gas. A good example is ice. Ice is made of molecules called H2O, you know that. All the H2O molecules in ice are tightly bound to give ice a very regular solid structure. When ice turns into fluid form, or rather into liquid form, we still have H2O, but the H2Os are weakly bound, but still bound, but they are weakly bound. They are stuck to each other, but they are weakly bound. Consequently, in liquid form, water does not have a definite shape. So, liquids take the shape of the container they are in. That is a fluid. A gas is also a fluid. The principles we are learning are not restricted to just liquids, they are restricted to fluids. So, they will apply to gases as well. You will come across some of these principles in physics 5D when you do thermal, because there we will talk about gases. Keep this in mind. Principles you are learning here extends to gases, not just liquids. We are talking about fluids. Now, let us talk about the gaseous state of ice. That is water vapor, correct? That is gaseous state, but when we say water vapor, it is still H2O, just that two molecules of H2O in water vapor form are not stuck to each other, are not bound to each other, but in water form two molecules of H2O are stuck to each other, weakly stuck to each other. In solid form, they are rigidly stuck to each other. So, the definition of a fluid is a state of matter where the molecules are bound to each other, but are weakly bound to each other or not bound to each other, as in the case of a gas. Now, what is an incompressible fluid? An incompressible fluid is, if you have a fluid in a zone, it is not easy to compress it. It is not readily compressible. Can you give me an example of a fluid that is incompressible, or a fluid that is compressible? Yes, water is incompressible. A fluid that is incompressible, a fluid that is compressible, air. You agree? Water is incompressible, air is compressible, right? When you go home, try to find a water bottle that is easily compressible, not like a flask like that, not something that is very hard, but the plastic can be bent. Tighten the cap. Seriously, do this experiment at home. Tighten the cap tightly so that there is no leakage. Try to compress that water bottle. Will you be able to compress it if you close the cap? If you do not allow the fluid to escape, you close the cap, will you be able to compress it? Try it. You will not be able to compress it. That tells us air is incompressible. That is why the tires in your car work, correct? You pump air and you sit in the car, you load up the car. If that air were to be compressible, you would have a flat tire as soon as you sit in the car. Am I right? We pump air in the tires. Air is incompressible and therefore tires work the way they do. Now, there is nothing called incompressible. It depends on the amount of force and heat and pressure and temperature. So, there are all these things that exist. So, if you change the temperature, if you exert an inordinate amount of force, then perhaps you will succeed in compressing. But we are talking about in regular flow, whilst the fluid is flowing, is the fluid compressible or not compressible. So, in incompressible fluids, and I should actually add one more word, because we are not going to deal with these special cases in our course. It is for a proper course in fluid dynamics, not a, I should not say proper course, a more advanced course in incompressible and non-viscous fluids. Actually, I should not add non-viscous here, just incompressible is fine. The flow rate will be constant. Let us understand why the flow rate will be constant, because what is flow rate? Flow rate is the volume flowing per unit time. So, even if it is viscous, but the fluid is not compressible, look at my hand everyone. There is a chunk of fluid over here, there is a certain amount of volume of fluid over here. This fluid moves over here, but the shape of the pipe changes. Let us say the pipe was like this and the pipe becomes this broad. Then the fluid that was here, the amount of fluid per unit time, when you go over here, you should have the same volume. How can the volume change? It is not compressible. The space taken is the same as the fluid moves on. Is that making sense? And therefore, if the fluid is not compressible, that is, if you cannot change the volume of a section of the fluid, the total volume, not the length width, but the total volume, if you cannot change it, the flow rate must remain a constant. And therefore, that is a very important point. In incompressible fluids, the flow rate is constant. That means you can have a very complex set of pipes through which a fluid is flowing through, but there is one thing you know, if you know the flow rate at any one point, the flow rate is exactly the same at all other points. This does not mean that the velocity is the same at all other points. But now you can intuitively answer the question, if flow rate is constant at all other points and the pipe's diameter increases, what will happen to the speed? Decrease. If the pipe shrinks in diameter, speed will increase, and therefore, you would see nozzles have a smaller diameter than the container that carries the fluid. You want to shoot a jet with a high velocity, all you need to do is bring it with a large enough diameter pipe and then give it a tiny nozzle, come out with a high speed. Why? Because you should brought down the area, flow rate is a constant, speed will go up immediately. So, this is a very important concept as far as flow rate goes, and we will remember this concept as we continue learning in this lecture. Yes.
So, sorry, I think I got lost a little bit there. You're saying that gases are incompressible fluids?
Air is incompressible fluids. Yes, and most gases are incompressible fluids unless you do other things with the gas. For example, change the temperature of the gas, change the pressure on the gas. If you make those changes, then you can alter the volume occupied by the gas.
So the state of incompressibility is just a state that any fluid can be in at a given temperature and pressure, essentially. Once it's like completely.
Any gas can be in, yes, or a liquid can be in, yes, yes. It is subject to temperature and pressure, but in 5B we do not talk about temperature, we talk about temperature in 5D, and it depends whoever is teaching it if they make that connection with it, but you should remember that the concept applies. Yes, yes.
If the problem doesn't state otherwise, should we assume that the fluid is incompressible?
Correct. If it does not say in our course, good point, let me write that down. In our course, we will only consider incompressible and non-viscous fluids. We are not going to consider the effects of viscosity in our class, because there are actually a lot of wonderful applications to talk about with non-viscous fluids and incompressible fluids. The case of viscosity, where you have things like glue flowing, for example, or molten lava flowing, that is viscous thing flowing, that is a separate matter. But it is a very easy to draw an extension to what you are learning here in that case. So, it is best done in a different course. Okay. Now, the concept of flow rate out of the way, I will take on one of the most important concepts that applies to both static and moving fluids. But before I do that, I need to make two quick announcements. First of all, if you joined the course late or are still waiting to join the course, are either waitlisted or are not able to waitlist because of any issues, you should come see me. Some of you met with me on Monday and filled out this sheet. I have emailed some of you. If you did check your emails, if you did not get an email from me, come see me right after class today. Sounds good? This applies to others too who are not yet enrolled. Next important thing, Expert TA is now up and live. I posted an announcement on Canvas, a very detailed one with instructions on how to enroll. Please go through that announcement. I need everyone enrolled before class on Friday. Sounds good? Now, not just enroll, there is a very simple assignment. The first assignment is how to work with Expert TA. Most of you probably know that already. Even if you do know, do it, because it is the easiest assignment in which you can score 100%, and it is counted toward your grade. There will be no extensions on this assignment. So, it is a very simple one. How do you access hint, how do you access feedback, etc. It may ask you to make some deliberate mistakes. Go ahead, make those mistakes. At the end of the quarter, when I download the grade book, all those of you who complete that assignment will get 100% on it. So, do not worry about the grades you are getting because you are making a mistake here or there. But I want everyone to get used to it, and if you are facing any issues, I want to hear about all those issues by Friday, not next week. Sounds good? So, get started with it, and get started with the first assignment on Expert TA as well, which is on fluids, which you will be able to do. I will tell you how far after I cover some content today. I already did one very important concept. Now, we will learn about the next concept. Okay. The concept that we are now going to learn, which is extremely important, is this. What principle? This means a method or a problem solving tool relates fluid properties between two points. For both static and moving fluids. And the principle, you can already see what would happen if it is moving fluids. moving fluids 2 points, what principle applies? Work net or energy conservation, because we are now, if they are moving fluids and we have 2 points, we are trying to relate 2 speeds at 2 points, and like we know, if we have a problem where we have to connect the 2 speeds between 2 points, the way to attack that problem is by using the concept of work net equals change in kinetic energy or conservation of energy, whichever you are comfortable with. Sounds good? So, we can already see that, but it turns out that that principle of work net equals change in kinetic energy would apply even for static fluids. That is not obvious to see, but I will show you why. Sounds good? So, first let us write down the name of the principle, but remember, merely knowing names is completely useless. That is like jargon. You have to know what it means and what to do with it. So, the name of this principle is Bernoulli's principle, Bernoulli's equation, blah blah blah. I will tell you today, write this down. You are 100% guaranteed the derivation of Bernoulli's principle on the first exam, 100% guaranteed. One question you know is on your exam, derive Bernoulli's equation. So, focus on this and learn it. I will not give Bernoulli's equation as a formula in the formula sheet. It is a complicated looking equation, but it can be derived quickly, and I want you to learn how to derive it. There is a lot to learn as you go about deriving Bernoulli's principle. The first thing is, and it is a very common question I like to ask, what does Bernoulli's equation tell us, or what does Bernoulli's equation quantify? There is a very simple answer, and this is a conceptual answer that you should give so that you can do the derivation. The answer is you will lose points if the word transfer is missing. It is not energy per unit time, it is net energy transfer per unit time. This is what you should think when you are thinking about Bernoulli's equation, either now or later in your career. You are thinking, what am I doing? Aha, I am trying to document how is the net energy being transported per unit time. This is what we are doing. While doing this process, it condenses down to a really elegant, not necessarily too simple, but a really elegant expression, and you will see that now. So, since we have to do net energy transfer, you remember from physics 5A that energy transfer, a word, actually means the physical quantity of work, correct. Work done by a force is the energy transferred by the force. Here we are talking about the net energy transferred, so we have to think about the work done by the net force. Work done by the net force per unit time. Sounds good? So, this is how the derivation of Bernoulli's equation starts. If you get a conceptual question, what does it quantify? You should write this. It is the net energy transfer per unit time. I say derive Bernoulli's equation, you are going to do something else now. So, to derive Bernoulli's equation, we do the following. We start by saying we need to execute This is net energy transfer, work done by the net force. For the moment, I will just write it out. You can just write work net, but really this means work by net force over time. But you ought to remember that when the net force succeeds in transferring energy, it leads to change in kinetic energy. So, work done by the net force is the change in kinetic energy at 2 points, 2 speeds divided by time. This applies to all fluids. Bernoulli's equation covers all fluid motion. It is not restricted to regular pipes or cylindrical pipes. It applies to any fluid between 2 points. There is a fluid in this room, you can relate fluid properties at this point, tip of this finger and that near that light bulb. You can use Bernoulli's equation to relate the fluid properties between these 2 points. It does not have to be a pipe, but it often helps to do the derivation with a well defined geometry. Otherwise, it becomes really messy and complicated to execute that derivation. Is that making sense? So, what we will do is we will do the derivation of Bernoulli's equation using a well defined geometry, a pipe. Now, what I will do is I will choose a pipe whose width is changing, deliberately choose a pipe whose width is changing. So, let us draw a pipe whose width is changing. It does not matter whether you make the lower part broader or the upper part broader, it does not matter. So, let us say for example, we choose a pipe like this. Make sure the pipe changes height, because it is very versatile. It is not necessary that the fluid be in the same level, fluid can change height. So, and then the pipe becomes thinner at the top, give it some room over there. Draw this diagram big because you will need labels in this diagram. Make sure that the base is broad and big, and then connect the pipe. This is the framework of a pipe whose width is non-uniform. Now, what happens here is if a fluid has to flow, for example, suppose there is a fluid over here, you want the fluid to get up over there, what do you have to do? Okay, suppose there is a fluid over here and there is no block, what will this fluid do? Go down. If the fluid is over here and there is no block, will the fluid climb up? No way. So, what do we have to do? Push, apply a force. With fluids, what do we do with force? Write them in terms of pressure, apply a pressure. So, when we have fluids, we are thinking I need to apply a force, consequently this means I need to apply a pressure, and if I apply a pressure over here, it is going to come out over there. It can come out of there if I apply sufficient pressure, correct? Not just any pressure. You guys good with this? Following? Now, so what we will say is that as such, in order for the fluid to move from one point to another point, we have to apply some pressure and some force. We will first think in terms of force, then convert all the force terms into pressure and so on and so forth. So, we will say that suppose we have a cross sectional area over here, and I say this area is A1, I apply a force F1 like this on a chunk of a fluid, and let us say I define a chunk of a fluid as this much, this chunk of the fluid. Then this chunk of the fluid has a thickness delta x 1. As this fluid climbs up, or not just this fluid, since it is incompressible, if I push over here, since it is incompressible, this volume will not change, this fluid will push the next segment of fluid over there, the next segment of fluid over there, next segment of fluid over there, correct? This is going to happen. But now I have this chunk over here, this is the volume. Since flow rate is a constant, if this fluid moves, which it will if I push, the same volume must move over here. So, are you able to see that because A is smaller, the length will be larger? So, this equivalent volume can be found out here over a larger length. And so, I am going to go over here and say this means that when I push this fluid here, because it is incompressible, the same volume is going to try to come out over there. Are we good? So, let us mark this. On this side, I will say this part has a cross sectional area A2, but is now going to take up this much length over here, and that length is delta x 2 is the length of fluid that will move over there. Sounds good? Now, imagine, why do we use these, where do we use these things in cases where we want to pump something up from some lower level, base of a lake, get the water out of the lake to provide resource to the city, or base of a well, get it out to water a farm, right, something like that. That means when this water comes out at the top, it has to come out somewhere, generally air, but it does not have to be air, it could be into another water tank where there is water. But no matter what it does, when it tries to come out, when this section tries to come out, are you appreciating that the force on the section, not by the section, the force on this section as it tries to come out is backwards from the environment. This is a push by an external agent onto this thing, but when this thing tries to come out, it is trying to come out into the environment, which means the environment is going to push back onto that element. And so, this guy is experiencing a force this way over here, F2. So far so good? This is the basic structure. Now, in any work net or energy transfer problem, before we do any work business, we must document all the interactions, which means all the forces, correct? We have documented two forces on the chunk of fluid. One force is F1, the push at the base. One force is F2, the push from the environment as it tries to come out. Are there any other forces on this chunk as it goes through the pipe? Yes.
When you drew the second force, force 2, why is it getting a push from the environment?
Because it is the water trying to come out of the pipe. When it tries to come out, it has to push on the environment to come out. When air comes out of a pipe, water comes out of a pipe onto air, it is pushing on the air, but on the water the push is from the air backwards, Newton's third law. It is pushed back onto the water. We are modeling the flow of the water. We are not modeling what is happening to the air outside. We are modeling what is happening to this guy over here, and we are documenting all the forces on this chunk. So, one force on this chunk is here, because there is a push from something down here. What gives that push? We will come to it later. Some pump is pushing onto it, some pump is applying a pressure over here, and then when it tries to come out over here, it has to fight whatever environment you have over here, unless you have vacuum out there. Yes? No, no. These are not action reaction pairs. These are action reaction pairs right here. The force this guy exerts on that is equal to the force this guy exerts on that. Okay. What are there other forces on this chunk of water? Gravity, exactly. It's going from here to there. So there is gravity. So we can say, we can imagine a similar chunk, same size, but perhaps like this, same volume. This volume, that volume, that volume are all same. Let us draw a free body diagram over here. There is the force of gravity on this chunk of water. Is there any other force on this chunk of water?
Is there a friction force from the interior of the pipe?
There is no friction because we said it is non-viscous, so it does not stick. So there is no friction, but there is normal, exactly, there is normal force, and the normal force is not at all easy because it is making contacts in all different directions. It is not like a block on an inclined plane with just one normal. But let us, whatever it is always going to be something, say, like this. Let us draw this for the moment like that as the normal force. It is always going to be perpendicular to the surface. It could be pointing this way, it could be pointing that way, it could be pointing this way or that way, always perpendicular to the surface. That is the definition of normal force, we know that. So the next step is to take this forward and write this. Those of you sitting so close, you will not be able to see what I write over here, and I have to write over here because of how much the board covers. So, but perhaps I can change this a bit and write this is going to become work net over time is Ke2 minus Ke1 over time, and when we do that we should mark the 2 points like we did over here, point number 1 and point number 2, and so we have these 2 points over there. Now on the left hand side you must document all the work terms in here, and so we will write we have work done, sorry, this will not get recorded. So from this we will write work done by force 1 plus work done by normal plus work done by gravity plus work done by force 2 equals Ke2 minus Ke1 over time over time. Are any of these works 0? That is a very important thing to do very early on. If anything is 0, get rid of them. Are any of these terms 0? Answer quickly. Yes. Normal force is not 0, but the work done by the normal force is 0. Why is it 0? Because normal force is perpendicular to the direction of motion, or normal force has no component in the direction of motion. And you should all remember that work is not force times distance. It is high time you banish this from your head. And so normal force is not 0, but the work done by normal force is 0. The next thing is we will write what is work done by force 1. Work definition is component of force in the direction of motion times the displacement. So in this case work done by force 1 is F1 delta x1, and is it positive or negative? It is positive because F1 and the movement delta x1 are in the same direction. So this work is positive, and we will simply write this is plus F1 delta x1. Work done by gravity. You I do not know how much you remember, but it is extremely important to review and remember how to write work done by gravity. Work done by any conservative force is to be always written as the negative change in potential energy due to that conservative force. And for gravity, the potential energy is mgh, and consequently the work done by gravity must always have this minus sign, no matter whether you go uphill or downhill, minus u2 minus u1 due to gravity. So, this should be minus mgh minus mgh, essentially becomes minus mg h2 minus h1. This minus sign is extremely important for work done by gravity. So, we will write for gravity, this is minus mg h2 minus h1, work done by force 2 is minus F2 delta x2, not F2 delta x2, because F2 is pointing this way, delta x is that way, there is a net minus sign in there. This divided by time is Ke2 minus Ke1 divided by time. Now comes the trick that I showed you last time, that is, all force terms must be converted into pressure terms, all mass terms must be converted into density terms. I am going to erase that figure now. So, taking this forward, we see that we can write this term over here as pressure at point 1, area at 1, delta x1 minus mass will become rho times volume g h2 minus h1 minus pressure at 2, area at 2, delta x2 the whole divided by time equals Ke2 minus Ke1 over time. Actually, perhaps it is better to write this as half m V2 square minus half m V1 square over time. Now, what do you see this guy is becoming? A1 times delta x1. What is A1 times delta x1? Volume 1. What is A2 times delta x2? A2 times delta x2, volume 2, area times a length. Area times a length is a volume. So, the next thing will become, this is becoming P1 V1 minus rho V G H2 minus H1 minus P2 V2, that is it, divided by time. But now I am going to write this in a slightly different form, a very slightly different form. It is divided by time. So, let me divide each of them with time, because it is divided by time, and this is going to be half m is going to become rho times v divided by time v2 square minus v1 square. So far so good. What concept to use now? Very important concept to apply, otherwise you cannot get Bernoulli's equation. What is this extremely important concept to apply that you learned today, without which you cannot get Bernoulli's equation? Not the, more than the volume flow rate, the volume per unit time, that is the same. That means V1 over T is equal to V2 over T is equal to any V over T. Consequently, we can just divide by V over T, and V over T will disappear from this equation. Bernoulli's equation has no volume ultimately. There is no flow rate involved in Bernoulli's equation, and that is because you observe V1 over T is equal to V2 over T is equal to V over T. So, divide by V over T. And if you divide this equation with V over T, and this is why I do not like this board, keep erasing. If you divide this by V over T, you will get P1 minus P1 minus rho G H2 minus H1 minus P2 equals half rho V2 square minus V1 square. As such, this is Bernoulli's equation. This is not how it is known, but this is Bernoulli's equation, where we have connected. Watch what Bernoulli's equation connects. What is it about? It is about energy transfer per unit time. What does it connect? It connects the pressure, the height, and the velocity at one point to the pressure, the height, and the velocity at the other point. Are you seeing that? There are two pressures, there are two heights, there are two velocities. So, Bernoulli's equation is used when we want to relate the pressure, the height, and the velocity at one point to the same quantities at another point. So, what we do now, since it is about one point and the other point, we just collect all terms for one point on one side, all terms for the other point on the other side. And so, just rearranging, we write this means P1, look at my finger please, minus minus plus rho G H1. This again, look here, half rho minus V1 square. I am going to take it on this side by adding this term. So, this is going to be plus half rho V1 square, all one terms on one side, equals P2, negative P2, add P2 on both sides, P2, negative rho G H2, add rho G H2 on both sides, and then I already have plus half rho V2 square. This is called Bernoulli's equation. What is it? What is Bernoulli's equation? The net energy transfer per unit time. This is what Bernoulli's equation quantifies. What does Bernoulli's equation connect or relate? It relates the pressure, the height, and the velocity at one point to the pressure, the height, and the velocity at the other point, with a very, very important concept ingrained within it, the constancy of flow rate. Sounds good? Yes.
Sorry, why does V1 equal V2 equal V?
V1 does not equal V2 equals V. That is not what it is saying. What is it saying? V1 per unit time equals V2 per unit time equals V over unit time, because flow rate is a constant. V over T is a flow rate.
Okay. So just because we have that over T, we can say that the flow rate is constant at all places.
Yes, that is an independent concept. Flow rate must be constant if the fluid is not compressible. If the fluid is compressible, you can alter the volume. But if the fluid is incompressible, you cannot alter the volume, then the amount of volume being transferred per unit time must be the same. The same chunk must move around. and we exploit that in deriving Bernoulli's equation. We say we are going to write in terms of what we are familiar with, that is work and forces and displacement and kinetic energy, but then we are going to make some applications. Number 1, substitutions. Replace all forces with pressure, but not just change force to pressure in terms of pressure. Write all masses in terms of density and connect the concept that flow rate must be constant. You do that, you derive Bernoulli's equation. This is a guaranteed problem on the exam. You must start practicing it today. It is a very easy derivation actually. Just practice a few times. You won't be able to do it right away, right after class. You will do this in section and then just practice, and we will get to that. One last comment. We will take a numerical example in class, but write this down. The concept of power. Watch this. This is fun. You should remember from physics 5A, what does power mean? Power must be associated with a force. Power due to a force F is the work done by the force F divided by time. Essentially, you can see Bernoulli's equation is kind of a relationship on power is hiding in there in this. Now, we can write work done by a force as force times displacement over time. And then we can write force in terms of pressure and write that this is equal to pressure times area times some displacement over time, especially in a cross section in a regular pipe. We cannot always write, this is only true if we have a regular pipe. Just 1 minute. This guy is volume. So, you can see something very nice in here. Power due to a force F is equal to the pressure due to that force, times volume over time. What is volume over time called? Flow rate. So, if you know the flow rate and you know the pressure, you know the power. Is that making sense? So, we can derive power very quickly by writing these two lines and then saying power is therefore pressure due to the force times the flow rate. The power will have the same unit that we have seen in 5A, which is what is the unit of power? What? 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 All right. Have a good time in section. Get started with expert TA, and if you are not yet enrolled, you should come see me.
Hello.
Hi.
I just wanted to let you know that I have
Yes.
a chronic illness and I sometimes can't predict when I'm not going to be in class. I'll definitely make sure to email